everyone, welcome back. If you haven't heard me introduce myself earlier today or yesterday, I'm Amelia Adcroft. I'm the president of Oxford University's Physics Society. And the last speaker we have for our conference today, we hope you've enjoyed the rest of it. But today as our final talk, we're going to have Professor David Wark from Oxford speaking about neutrinos. So I hope that you enjoy the last talk of our conference, that you've enjoyed all the previous ones. You can put questions if you have during the chat in the into the Zoom chat, as well as joining our Slack channel, where Professor Wark should be available to answer questions afterwards. And we believe that Professor Wark might be giving some talks to our Physics Society next Wednesday and the Wednesday after. So if you enjoy this talk, we hope you'll come and hear even more about his work on neutrinos in the future.
All right, thank you very much for that introduction. Hello, everybody. Thanks for coming by this afternoon. Let me see if I can make the technology work here. Okay, we go there, and then we hit that. And does anything happen? No, because we're, whoop. Okay, come back here. Where did you go? There we go. I hope you're now looking at the slideshow. So yeah, I wanted to give you a brief introduction to a few of the experiments that we're working on in Oxford and in the UK that have to do with neutrinos and specifically neutrino oscillations. Now, the theme of several of the other speakers that I've heard have been physics beyond the standard model. And I'm in a kind of an easy position because I've already got it. I don't have to look for physics beyond the standard model. We already have it. And for that, I will present as evidence. I first was introduced to the standard model sort of formally in a course when I was a graduate student at Caltech in 1981, taught by Barry Barish. And at that point, I wrote down in my notebook the standard model. I tried to scan that notebook page and use it instead, but it's done in you know, those old automatic pencils we used to use. And it's so faint, you can't really see it. So I've got Fermilab's diagram instead, but it doesn't make any difference. They're identical. These are the particles of the standard model, as I wrote them down in 1981. There are the 6 quarks, the 4 gauge bosons, the 6 leptons, including the 3 neutral leptons, the neutrinos. Let me see if I can make that a bit more visible. We have the neutrinos here, and of course we shouldn't leave out the Higgs boson. Whoop, come on, you. The Higgs boson. And in 1981, when I was taught the standard model, the neutrinos, you know, had the following properties. They were considered to be 3 neutrinos with a distinct and a conserved lepton flavor number, which meant an electron neutrino. A nu E was always an electron neutrino and would always give rise to a neutrino, to an electron if it interacted, and so on, a nu mu nu tau. They were strictly massless, and they were strictly left-handed. Okay. Now, in 1981, when this was written down and when I was taking this class, it required a certain eye of faith to believe in all of this, because at that point, no one had ever seen a tau neutrino. Nobody had ever seen a top quark, for that matter. Nobody had ever seen the Z or the W, the gauge bosons of the weak interaction, and certainly no one had ever seen a Higgs. Okay, so, you know, you might look at this and think we're taking quite a bit on faith because, you know, there's a lot there that's missing. However, the indirect evidence that we could obtain at lower energies pointed very strongly towards not only the existence, but in some detail, the properties of all of these other particles. And sure enough, in the intervening 40 years, all of these things have now been found. The the Z and the W were found by UA1 at CERN, the top quark by CDF at Fermilab, the new tau by Donut at Fermilab, and the Higgs boson, of course, famously a few years ago, well, more than a few years ago now, at CERN. And so everything on that side of the standard model has come out exactly as predicted. It's just exactly what we expected it to be. Everything I wrote down in my book in 1981 has proved to be true, and nothing has been added to it. On the neutrino side, on the other hand, this is all crap. None of it's right. And so in that sense, the physics we have discovered in the intervening 40 years that demonstrate that's all wrong is physics beyond the standard model. Now, the interesting question is how far beyond the standard model, and we'll come back to that a bit as we go along. Right, and so how did we show things beyond the standard model? Well, I've got a half an hour, so it's a little hard to put 40 years of work by, me and originally a couple hundred and now a couple thousand of my closest friends into 40 years. But so we'll do the old montage. We have with a large number of different experiments. First, the original solar neutrino experiment, some of which were already running in 1981. Well, the chlorine experiment, the Davis experiment, followed up by the Sudbury Neutrino Observatory, which was built in Canada, where Oxford was very heavily involved in this. Superchemia Canada, looking at atmospheric neutrinos. CAMLAN, looking at the disappearance of antineutrinos from reactors. And the combination of all of these, now combined with a long list of other experiments, have demonstrated that neutrinos are not massless. They have mass, and they do not have a conserved lepton flavor number that they mix. Okay, and because they have a mass, they're therefore not strictly left-handed. So none of those things that were believed about neutrinos in the standard model in 81 are true. So, hurrah, wonderful, prizes are handed out like confetti. Everybody's happy. These show National Medal of Science being given to Ray Davis, who subsequently shared the Nobel Prize, Masatoshi Koshiba, Takeaki Kajita, and Art McDonald winning the Nobel Prize for physics for Superchemia of Canada and Snow. And this is them plus a number of other people who won the Breakthrough Prize in physics in 2016, along with about 1,000 people, myself included. Most of the neutrino physicists that you ever talked to won the prize, which led a science journalist to identify these 7 gentlemen as the rock stars of physics, which tells me that science journalists don't hang out with a lot of rock stars. So, that brings up the question, are we done? And of course, the answer to that, as frustrated science bureaucrats who have to continue to fund you will always tell you, never, right? In science, answering any set of questions inevitably leads to more questions. And that's kind of especially true when you're studying the standard model, because as I assume was pointed out to you at some point in your course or earlier in the day or whatever, despite our immense pride in the standard model, it is a low energy effective theory. By construction, the standard model cannot be a final theory of nature. I mean, to renormalize it, you have to add in some physics at some higher scale, right? So something lies beyond the standard model. And you know that not just because there are these things that we can't explain, like, what is dark matter, what is dark energy, but just in the very construction of the standard model, as it is written down, it is not a final theory. So there must be stuff beyond it. And no matter what you discover, you have to keep probing to try to find out what lies beyond. So specifically in neutrino physics, we have a number of open questions. I'll come back to the next one in a minute. What is the pattern of the masses of neutrinos? A big question, and that's the main topic of this talk, is, are oscillations the same for neutrinos and antineutrinos? In the previous talk, you heard about the LHCb experiment, which is one of the world's premier tools to look for CP violation, the violation of the CP symmetry, which says the laws of physics should be the same for matter and antimatter. Is that true in neutrino oscillations? And also, we've shown that neutrinos have mass, but we haven't measured their absolute masses. By the weirdness of oscillations, which are an interference phenomena, we can only measure the difference in their masses. We don't know their absolute masses. And we don't even know, perhaps, one of the most basic questions you can ask, are neutrinos equal to their own antiparticles? That might seem like an odd thing to ask, but there's nothing that prevents it from being true. And in fact, even before any of this was done, before the neutrino had even been observed, a fellow by the name of Ettore Majorana had stated that this was a possible solution, because a positron can't be the same thing as an electron because they have opposite electric charge and so on. But neutrinos don't have any additive quantum numbers, at least as far as we know. So there's nothing to prevent a neutrino and an antineutrino from being the same thing. And that is one of the biggest questions we attack. Now, the experiments I'm going to tell you about sadly can't do either of these last two questions. Although I once said that in a big meeting in Germany, and this very proper old professor in the back stuck up his hand, and I said yes, and he said, "You have not read my paper?" And oh well, I apologize. I will read you. So then I went away and read his papers. So now let me modify my statement. Neutrino oscillation experiments cannot observe the absolute mass of a neutrino unless we observe neutrino oscillations from a source which has been gravitationally lensed. So we would have to see neutrino oscillations where the neutrinos came from some galaxy at the Hubble distance and then got lensed. And I will await my great grandchildren pointing out that that experiment can't be done. So anyway, we're probably not going to do that with an oscillation experiment. So those are other experiments which I may allude to in the following weeks, but I won't talk about today. Let's talk about these first two questions, the pattern of masses and the matter antimatter. So first on the pattern of masses, like I said, a neutrino oscillation experiment measures the difference in the masses, but what's actually worse, it measures the difference in the squares of the masses, which means not only can't it tell you the absolute mass, that it can't in principle even tell you the sign of the differences of the masses. And so we have two solutions which are consistent with existing experimental data from all those experiments I just told you about. There's this one with a pattern of masses where the difference between these two, now notice these are nu e, nu mu, and nu tau, the things you've heard of. And there's a nu 1, nu 2, and nu 3. So nu e, nu mu, and nu tau are the things with well-defined weak interactions, and nu e couples to an electron. Nu 1, nu 2, and nu 3 are the things that have well-defined masses, the things that will propagate in a vacuum. Okay, the eigenstate of the free particle Hamiltonian. The eigenvalue of that is the mass, right? And the things with well-defined masses are nu 1, nu 2, and nu 3. And the total weirdness, welcome to the world of quantum mechanics, is no rule says those two groups of three things have to be the same thing. They are in fact a mixture of each other, okay? So the colors show you the mixtures of the nu e, nu mu, nu, and tau that go into the nu 1, nu 2, and nu 3. And this sort of shows the pattern of their masses. There's one small splitting here of 7 10 to the minus 5 eV squared, and a larger splitting here of about 2.5 10 to the minus 3 eV squared. Probably. Although the data is perfectly consistent with another solution where two of them are heavy and one of them is light. Okay, and this one's called the normal hierarchy, and that one's called the inverted hierarchy, because people say, well, this looks unnatural. Why? Well, if we look at all the other fermions, as you go up in family, the mass splittings get larger and larger as you get bigger and bigger. So this looks like the other fermions. So people will say this is unnatural. And as a person who's spent most of his career in neutrino physics demonstrating that what theorists expected is not true, my response to that is, does that look natural? Okay. nature decides what's natural, we don't. And so to choose between those two, you have to do experiments, okay? And the experiment in particular you have to do is because of that business I told you, the oscillations only measure the square of the difference of the masses. You have to measure something which depends on the mass itself. And to do that, we have to measure the oscillations in the presence of matter. We have to see something called the matter effect. And that comes back into it later. Then the question of CP violation, as you know, in the early universe, we passed through a period of very high energy density, which we call the Big Bang. And as the universe began to cool, matter was produced via reactions like two gammas go to proton, antiproton, and a gabillion others I could write down. But the key thing is that in the standard model of particle physics, all of those reactions almost conserve the amount of matter and antimatter. As you know, there is CP violation in the standard model, but it's very small and it's nowhere near big enough to produce the matter and antimatter we see in the universe today. Because in the universe we see today, there is a enormous preponderance of matter over antimatter. So that means we're looking for places where the laws of physics do not conserve CP as a hint to where this may have come from. And neutrino oscillations are one such place. There's a model called leptogenesis that would perhaps explain where the matter-antimatter asymmetry arose from. And it makes sort of two low energy predictions, one of which is that neutrinos must be Majorana for leptogenesis to be, well, I wouldn't say true, but plausible. And similarly, it probably would mean that we would see CP violation in oscillation experiments, although that's not actually certain. So we want to look to see if oscillations are the same for matter and antimatter. So that brings me to an experiment that I've now been working on for 20 years, mostly upper level undergraduates, right? Which means you're mostly about 20 years old. So I started on this particular experiment about the time you were born, which teaches you another thing, that if you're going to be a neutrino physicist, you have to have a very long attention span, okay? And so what is this experiment? Well, we have this experiment I've already mentioned, superchemiocanda, which is an enormous tank of water. It's 40 meters in diameter and 40 meters high, buried under Mount Akenayama near the west coast of Japan. And it was originally built to look for proton decay. We'll come back to that. And it received half of a Nobel Prize for observing neutrinos that come from atmospheric neutrinos and observing that the number coming from above is not the same as the number coming up from below, or rather the flavor structure of the ones coming down from above and the ones coming up from below was not the same, which is a sign that neutrinos must have mass. This detector already existed, but on the east coast of Japan, they built a new facility called the Japan Proton Accelerator Research Complex, or JPARC, which was mainly built to do material science, chemistry, biology, that sort of thing, a big neutron scattering facility. But it also had this accelerator here, this ring that was built originally to do neutrino physics. And we repurposed this ring to as a neutrino source, okay? We did that so we could fire a neutrino beam from JPARC 295 kilometers across Japan underneath the ground to hit superchemiocanda, all right? And the idea was to build a muon neutrino beam using the proton beam at JPARC and look for the appearance of electron neutrinos in superchemiocanda. Now, originally, that was our main intent because it enabled us to look for the third kind of neutrino oscillation. When we started this, only two kinds had been seen. The third kind had not been seen. So originally, we built it just to do that. But that job being done and that third type of oscillation having been discovered, we also could repurpose it by changing the sign of the horn, the magnets that focus the beam, and changing the neutrinos from neutrinos to antineutrinos, and looking to see if the appearance of electron antineutrinos in a muon antineutrino beam was the same as the appearance of electron neutrinos in a muon neutrino beam. In order to do that, we had to make very sensitive measurements of the beam flux, the beam direction, the beam composition, because it's not possible using the techniques we did anyway. It's not possible to make a beam which is absolutely pure muon neutrinos. There will be some electron neutrinos in it as a contaminant, and those will be background, so you have to measure those. So in order to do all of that, we built a complex of near detectors at the JPark facility to measure the exact properties of the beam before the oscillations took place. And to give you a sense of the scale, this red magnet, okay, this is a clamshell magnet. In fact, it surrounds the entire thing. This is expanded. In operation, the whole thing is pushed together and this magnet goes all the way around it. That magnet is the magnet from the old UA1 experiment at CERN. It was decorating a parking lot at CERN, so they donated it to us. And we shipped it to Japan and stuck it 20 meters down in the ground to magnetize our near detectors. And that thing is the size of my house, roughly. I live in a 2-story detached house in Kennington. You've seen a zillion of them. It's the standard size for such things. And that thing is almost, it's quite cute. I want to superimpose it on a picture of my house, almost exactly the size of my house. So that gives you the size of the scale of these things. The complexity of neutrino experiments is getting similar to the complexity of a collider experiment from the last generation. Okay, and then you have Superchemiocanda, which is a giant tank filled with water, surrounded by photomultiplier tubes. These photomultiplier tubes are huge. They're 20 inches, 50 centimeters in diameter, sort of the size of an old television set. And here you can see 3 men in a boat to give you the scale of the detector. Okay, so why is this a good thing to do? Why would you build such a gargantuan thing? It can't be cheap to build such a gargantuan thing. I didn't point out it's a kilometer underground to shield it from cosmic rays. The reason is because this detector is enormous. It has 50,000 tons of water in it, but it can tell muons from electrons with incredible precision. And the way it does that is by looking at Cherenkov radiation. So when a neutrino interacts in the water, it makes, a new mu, makes a muon. That muon is traveling faster than the local speed of light. Given the energy of our beam, the muons are hundreds of MeV or GeV. They're traveling faster than the local speed of light in the water, meaning they emit Cherenkov radiation, which takes the form of a cone of blue light. And that cone of blue light goes out and hits the phototubes, and it makes a ring. So what you see here is this is the image of what is seen in the detector for a particular event. The detector, as you saw, was a cylinder. It was like a Coke can. So you take the lid of the Coke can, the top and the bottom, and you open them up. So that's the top and that's the bottom. And then you cut down one side of the can, you roll it out flat, and this is the rest of it. So that's a cylinder projected onto a flat piece of paper. And you can see this nice clean ring of Cherenkov radiation from a muon. An electron's much lighter than a muon, so it multiply scatters in the water. And when it does, your nice clean ring becomes fuzzy. And so you can tell electrons from muons by how fuzzy the ring is. And a test experiment was built at KK to verify this. At the 99% level, you can tell muons from electrons. So it's a fantastic detector for doing this experiment. Whoops, I just said all of that. Don't repeat me. Now, we tend to get up at these sorts of talks and, act like it's all easy. And then you might wonder, why did it take 20 years? It's not easy. One thing you have to do is you have to make a beam of neutrinos, and that's a very significant piece of technical effort. This is that accelerator I showed you. What we had to do, and we had to do this ourselves because the funding for this was not in the original design of the accelerator complex. So JPark said, sure, you can do it, but you have to build your own beam line. So we had to do this ourselves. we build a beam that bends the protons inside the ring. Those of you who know about magnets will say, wouldn't it have been a lot easier to bend it outside the ring? The answer is yes, but there's a temple right here, and we weren't allowed to build our detector in the temple, so we had to bend it inside the ring. You bend it inside the ring, you collide the protons with a target, which is a graphite rod, which is inside that titanium can right there. It emits pions. The pions are focused by these giant horn magnets that in operation, that target goes down inside that hole and has this magnet around it, a pulsed magnet, that focuses the pions that are produced forward into a long decay volume. The pions decay, making muons and muon neutrinos. And the muon neutrinos then go off, hit our near detectors, and then head off across Japan. So we here in the UK, we designed this target, and now we build them. We designed this window. This might not seem like a big deal, but that window has the highest intensity proton beam ever made by humans going through it in a pulse. And on one side of it's vacuum, on the other side of it is atmospheric pressure of helium. And if it breaks, the experiment's over. So it's a good idea for it not to break. So it's quite an engineering challenge. All of this stuff is hard. Don't have time to go into the details. We built these near detectors. Once again, I won't go through them in detail. They are a series of neutrino targets, which are bars of scintillator with either nothing or some metal in between them, which is used as a target for the neutrinos. By looking at the signals in the scintillator bars, we can reconstruct the track of the neutrino in there. And then there are TPCs, gas tracking chambers, between them to give us very precise measurements of the curvature of the particles, so very precise measurements of their energy. And then that's surrounded by an electromagnetic calorimeter to catch any gamma rays produced in the events or arising from the decay of things like pi naughts. And this whole thing is placed underground where the beam goes through it. And we very carefully construct this beam, and with great precision, we point it and we miss. We aim 2.5 degrees to the side of the detector. And for reasons I won't go into here in a half an hour, that actually gives you a better beam. It gives you a beam which is more tightly focused on the energy you want. Okay, we do all of that, and then we have to do a hell of a lot of work. The way you do the experiment, right, is you generate these neutrinos, and then you measure how many you see at the other end. And you have to compare the number you see to the number you expect. But to do that, you have to know how many you expected. And that requires us to make a neutrino flux prediction, which means we have to understand the beam in tremendous detail. It means we need to understand what the probability of a neutrino interacting with a nucleus is. And that requires us to understand nuclear physics theory in considerable detail. And we have to understand the performance of all our detectors. So we do all of that, and with the measurements we make at the near detector, we can predict how many events we should see at the far detector, and then we see how many events we do see at the far detector, and we compare the two, right? That is a very long story made very short. One of the things that has come up is that we've discovered that we're far more sensitive to nuclear physics than we thought we were. As we make this experiment more and more precise, we discover that when a neutrino scatters off a nucleon in a nucleus, the nucleon does not act like it's a free particle. The nucleon knows it's bound in a nucleus. And that alters the cross sections, all right, and alters our experiment. Now, in a CP violation experiment, that wouldn't matter if it weren't for the unfortunate fact that while we can change the neutrino beam to an anti-neutrino beam, we can't change the target to an antimatter target. We can't fill Superchemia Canada with 50 kilotons of anti-water, right? And so when we switch from neutrinos to anti-neutrinos, the rate changes by about a factor of 6. And it has nothing to do with CP violation. It's just the fact that even though we have an antimatter beam, we still have a matter target. So we have to correct that factor of 6 to a few percent to look for the CP violation. And so we're sensitive to things like this. So we spend a lot of time these days studying such effects, and it means we need even better near detectors in the future. That's something, a bit of a specialty of our group in Oxford. We have experts in this sort of theory. So I won't go through all the near detector measurements. I mean, even if this talk were a week long, I couldn't do it. We measure the events in different categories. These are charge current events, event with an outgoing muon or an outgoing electron and no indications of any other particles. These are ones with a charge current event that have a pion, multiple pions, and various other things. And what you see here is the data in the near detector, which are the points, compared to the prediction of the Monte Carlo, which are the histograms. And this is done out of the box. This is what we thought would happen. And after we got the data, we went back and retuned our Monte Carlo and our understanding of the physics and improved the situation to here. And the fit is much better, but you see it's still not perfect. So we have more work to do on understanding the beam in detail and understanding the interactions of neutrinos with matter in detail. But let us move on to the far detector. Here's the data we see in the far detector. This is a slightly old slide, but the details aren't different, or the basic thing isn't different. These are the nu mu's, and the dots are the data as a function of energy, how many nu mu's you see and how many nu mu bars you see. The solid curve is what you would have expected to see at Super Kamiokande if neutrinos didn't oscillate. So obviously, there's a bunch of ones missing. So this is, if you didn't believe neutrinos oscillated before you saw this data, you have to believe it now. But of course, that's not news anymore. What we're trying to do is compare this to this, or more specifically, we're trying to compare the appearance of electron neutrinos. Okay, what's plotted here is the energy versus the angle of electrons emitted in the detector. The data are the dots, and the prediction are the underlying heat map. And you see that for neutrinos and antineutrinos. So you compare this to look for CP violation. And the experiment got quite a bit of attention last spring when we released the most recent results at that time. That the results were on the cover of Nature. And here is the data. So what you see here, these are electron events appearing in the detector as a function of their energy. You see a peak. Okay, what is that peak? Well, that's the mirror image of that nu mu peak. I showed you that peak that you expected to see in nu mu's, and the nu mu's had disappeared. Well, some fraction of them turned into nu e's, and so you see that peak appear in electrons. So there's your peak. The reason that Nature stuck it on the cover was the colored histogram is the expectation. Okay, this angle delta is an angle that parameterizes how much CP is violated. If delta is equal to 0 or delta is equal to pi, then CP is conserved. If delta has any other value, then CP is violated. Okay, so we parameterize CP violation in terms of this angle delta. The prediction for delta equals 0 is shown here. Okay. And for antineutrinos, you have the data on the bottom. The data, once again, are the points. The histogram prediction is here. The orange is the expected appearance of electron antineutrinos. The pink, or the salmon, or whatever color that is the appearance of electron neutrinos. You can see there's a contamination of electron neutrinos in the antineutrino sample. And that's a consequence of the fact that we can't make an antimatter target for our beam. So there you will always make some of the wrong sign ones. But the thing that gets people excited is if you look at the data, you can see that the points are not consistent with the prediction, right? There are more counts in all the bins than there are in the prediction. So more electron neutrinos have appeared than you would predict. And conversely, in this one, if you add it up, there are fewer electron antineutrinos than you would predict. And this is consistent with CP being violated. And in fact, if you do the fits, once again, this is that angle delta CP. These are some mixing angles that say how much the neutrinos mix. And the area which is consistent with the data, the best fit is a delta CP of about minus pi by 2, which means that CP is as violated as it could be. Okay, so that got everybody excited, perhaps more excited than they should be, because, but you know, you got to put something on the cover. But if you look at the uncertainties, you can see that they extend over the region where delta is equal to 0 or pi. And so this data is not, you know, is not inconsistent with CP conservation. It just fits CP violation better. And I should tell you, there's a second experiment in this area called NOVA at Fermilab, which has the same intent. It's a very different design, but it has the same intent. And whereas prior to this article being published, they had also agreed that it looked like there was more CP, that there were more electron neutrinos in there, electrons appearing than there should have been. They took more data, and when they did, they no longer found that. They were now consistent with CP being conserved. Now, the two experiments have such large errors still at this point, they don't disagree with each other, but you get a very different inference by looking at them. With this one, it looks like CP's not conserved. In NOVA, it looks like it is. So what do we do about that? Well, we make snide remarks about each other in the bar, but to move the world further on, we need better and bigger experiments, okay? And so that's what we're doing. On T to K, we're upgrading that near detector. We have taken some of the TPCs and turned them around sideways, and we have taken our neutrino targets and changed them from bars to little cubes, so we could do 3D reconstruction of the events. And we're upgrading the beam to more than a megawatt, so it's more than a factor of 2. All of that so we can get more data. And then down here is this little line. When you think of science as this great grand enterprise, you don't realize how much grubby reality there is in it. This little line buried in a Keck report might seem like nothing compared to these wonderful detectors I've told you about. But it says that KEK will run our beam for 4 months a year for us to take advantage of these new detectors. That costs them, over the 4 years they'll have to do it till Hyper-K turns on, about $40 million. So this one little line in a report is them spending $40 million on us. Thank you very much, Japanese taxpayer. Meanwhile, we've upgraded Super Kamiokanda. Once again, the glories of physics include slopping glue onto bolts to keep the water from leaking out. This was all done so we could add gadolinium to the water in Super Kamiokanda, so we could detect neutrons, which give us additional information, which is useful for all the analyses of Super K. And mainly I talk about it so I can show a picture of myself inside Super K. So, you know, I do some things other than sit in my living room and talk. But in the end, we'll never do it with the detectors we have. They're just not big enough. We don't get enough events. So the idea is to build, okay, there was Kamiokanda, then there was Super Kamiokanda. So now we're going to build Hyper Kamiokanda. Who says we don't have imagination, right? We're going to build one 10 times bigger, right? You would think we'd do something cleverer than that, but we can't think of anything cleverer than that. So we're going to build one 10 times bigger. It goes under this, I told you Super K is under Mount Ikenoyama. We're going under Mount Nijugoyama, which I thought sounded really cool until the Japanese explained to me it translates as Mountain 25. So, you know, you would have thought they'd have some more romantic name for a mountain than Mountain 25, but nope, that's it. So we're building it underneath this mountain. It's in fact, 9 times the size of Super Kamiokande. It's another big tank of water surrounded by phototubes. And it will, when we look for CP violation now, we will have thousands of events, not a few hundred. And so we will get very clean signatures of the difference between neutrinos and antineutrinos. And we will see a difference or not, depending upon, whether we're right, whether our central value is right or Nova's central value is right. And I don't have time to talk about it, but such experiments, you'd be hard pressed to it. This thing costs about, by the time we run it and everything, it'll be about $1 billion. It's hard pressed to spend $1 billion for one thing, right? So it does lots of things. The original thing Super K was built for is look for proton decay. If grand unification occurs, then protons should be unstable. They should decay to electrons and pions. And so you look for that in such detectors. Hyper K will be by far the most sensitive detector ever built for that, and will be sensitive to lifetimes of order 10 to the 35 years. Note that the universe is about 10 to the 10 years old. So this is 10 to the 25 times the lifetime of the universe. And let's hope the damn things decay. And we'll do all sorts of interesting astrophysics. I really don't have time to go into this, but Kashiba originally won his Nobel Prize for observing neutrinos from supernova 1987A. So such detectors are great for looking for exotic and rare things from astrophysics. Meanwhile, I mean, this sounds like fun and it sounds interesting, which means we're not going to get the market to ourselves. Fermilab is not giving up with Nova. They are building a vastly ambitious, huge new experiment called DUNE. It consists of a 40,000 ton liquid argon tracking calorimeter. That's an amazing thing. In a mine in South Dakota, they'll fire a neutrino beam of similar kind of design from Fermilab, 1,300 kilometers to hit this thing. And the beauty of this detector is, unlike Super Kamiokande, which can only see charged particles, can't see neutral particles at all, and you can only get those rings. So it's not good at reconstructing complicated events because all the rings add up on top of each other. DUNE gives you images like this, right? Where you see, these are the tracks of particles. This is a prototype called microboon. And a neutrino has come in and it has undergone an interaction there. And there's the lepton going out, right? And that's the recoil proton and that's a pion. And so, you can image these interactions with unprecedented detail. And, hopefully from that, gain a great deal of sensitivity to the exact details of what's happening, which makes it interesting for this experiment. Maybe it's not, to be honest, on paper, it's not as sensitive as Hyper K, just because it's not nearly as big. But the thing that excites me about this experiment is Hyper K is very, very well designed to do the things it's designed to do. But the odds that it's going to find something completely unexpected are low because we've already had Super K. So, if there was something completely unexpected, probably we'd have already seen it. Nobody's ever built anything of this scale before with these capabilities. So, all the indications of neutrino oscillations came by accident looking for something else. Solar neutrinos, they were studying the core of the sun. Atmospheric neutrinos were background of proton decay. So the discovery of neutrino oscillations was an accident when looking for something else. And so who knows what we'll discover with such a new detector. So conclusions, I'm probably way over time. I unfortunately, my clock that normally says went away on this, but anyway. So neutrino oscillations are the first laboratory physics we've seen beyond the standard model. It may be far beyond the standard model if neutrinos are Majorana. We don't know yet. The parameters that govern neutrino oscillations, those angles and delta and the masses and all that, they're fundamental parameters of nature as far as we know. And so one thing we do is to try to determine those with greater precision to test models. The very smallness of neutrino masses may be hinting at physics of very large energies through something called a seesaw mechanism. I don't really have time to go into that. But in principle, studying neutrino masses at these tiny, tiny masses could give you access to physics at much higher scales than anything could ever be measured in a collider. So that's another reason to try to do this. Neutrinos are the second most numerous particle in the universe. So even if they have a tiny mass, it can have a cosmological consequence. So we have to try to find out what that is. And they may be pointing to the solution of the mystery of where the matter in the universe came from. We don't know yet. So, and the detectors that we build to study these things can be used for lots of other things: proton decay, supernova, the sun. We look, anytime anybody sees anything, a gravity wave detector, a gamma ray detector, or anything, we check to see if we see anything in super K. We haven't yet, but one of these days. So we have enough to keep us busy for quite a while. So thank you.
Thank you so much, Professor Wark. I know a bunch of people have been asking questions in the chat.
I can't see the. I think I have to stop sharing in order to see the chat. Do I or
yes,
don't I?
That's fine. So I can read them out. Although I know Lorenzo messaged me asking if he could say himself. So if you'd like to start.
Uh-oh. Wants to come after me or directly, huh?
No. I would never. So anyway, thank you so much for your talk. It was super interesting. So my question is maybe a bit off topic with regards to what we talked about today, but what is your opinion on neutrinos being, or at least being part of dark matter? Because that's an hypothesis that gets thrown around a lot, but I'm curious, what's your opinion about that?
Well, you know, the scientist in me steps up and says what the last scientist said, which was, well, we don't have opinions, we look at the data, which of course is crap, because we sit around in the bar and drink and we have lots of opinions. Obviously, neutrinos are part of the dark matter because we now know they have mass, the second most numerous particle in the universe. And so they are part of the dark matter. It depends on what that pattern of masses is, whether they're at all significant. And in this case, I'm not so much talking about the hierarchy, you know, whether there's two heavy ones and one light one, or two light ones and one heavy one. I'm talking about what the underlying mass is. The sort of naive thing is to believe that neutrino masses will be like all other fermion masses, and that the masses are of order the differences between the masses. So an electron is very light compared to a muon. So the difference between the muon and the electron mass is about the muon mass. And a muon is very light compared to a tau. So the difference between a tau mass and a muon mass is about the mass of the tau, and so on. If you believe that's true of neutrinos, then the electron neutrino has a tiny, tiny mass, right? And the muon and tau neutrino is very, very light. And if you add up the masses on that assumption, it is not a significant component of the dark matter. It'd be very difficult to see much effect from that. Although the most sensitive future experiments look comparing the cosmic microwave background radiation to the mass distribution seen in the universe potentially have sensitivity to that. We'll have to wait and see whether confounding effects, you know, obviously the universe has lots of things that happen to it other than neutrino masses. So we'll have to wait and see. But you wouldn't expect that to be a big effect. But there's no rule that says that has to be true. It may be the neutrinos are almost degenerate in mass, because you remember, most theorists don't believe that neutrinos get their mass from the Higgs mechanism the way the other particles do, right? Because then you'd have to explain the gap between this very light electron neutrino and the, you know, and the mass of the top quark. And, you know, it strains any symmetry that you try to come up with is going to bust if you try to put that big a gap in it. So often they believe that neutrino masses get their masses in other ways, the seesaw mechanism being one very, very popular model. Being, you know, popular doesn't make it right, but it's an interesting one. And if neutrinos get their masses from some other source, their masses may have a very different pattern. They may be degenerate. And in that situation, the differences could be small compared to the masses. And in that situation, neutrinos, the mass of neutrinos is set by our direct limits, which are about an electron volt, at which point they would be a significant component to the dark matter. If I had to guess, I would say they're probably not. But these days, when people talk about neutrinos as a component of dark matter, they're normally not talking about those neutrinos. They're saying there may be additional neutrinos, which are heavier, and escape all these other mass bounds by being sterile, by not having weak interactions. Such explanations are used to explain the fact that people don't understand their systematic errors in some, such explanations are used to explain certain interesting experimental anomalies. However, they strain the very edge of what you can permit in cosmology, because if you add such neutrinos, they affect the early universe, and they start screwing up the beautiful observed agreement between the predictions and the observations of the cosmic microwave background radiation. So if you want to bet a drink on it, I would say neutrinos are not a significant component of the dark matter, but it remains to be seen.
Thank you so much.
You're welcome. And I hope the next answer is shorter than that, or else we'll be here a while.
The next question was, if neutrinos were proved to be their own antiparticles, how could this difference from the rest of the fundamental particles be explained in theory?
Well, it really doesn't need to be explained. In fact, you almost have to explain the other one. I mean, there's an old saying attributed to some German physicist, I can't remember which one, who once said that anything which is not absolutely forbidden is absolutely required. So if you look at the standard model, it has dimension 4 operators. And if you look at the possible dimension 5 operators, there's one that could be added to the standard model without breaking anything. And that operator would be a Majorana mass term. It would give neutrinos this property that they are Majorana particles. And you know, I'm a firm believer in Occam's razor, because over my career, I have seen people write down a whole bunch of stuff and go looking for it and not find it. And I tend to hold to the most parsimonious explanation, or in the what I like to call Zatsepin's rule, a very famous Russian physicist by the name of George Zatsepin once in a very drunken party announced that he could predict the outcome of one of those early solar neutrino experiments that I worked on. It was in the Soviet Union. And he said that we would see 70 SNU. Okay, so the prediction with no neutrino oscillations was 132, and the prediction with neutrino oscillations was somewhere between, sort of 0 and, at that time, maybe 60 or 70. So he announced that the result would be 70 SNU. And I asked him, George, why 70 SNU? And he said, his answer tells you least. And he said that because if it was 70 SNU, you might just still believe it's something wrong with our understanding of the model of the sun. It's worth noting that the answer of the SAGE experiment turned out to be 72 plus or minus 4 SNU. So in that spirit, okay, the Majorana neutrinos require you to add the least to the standard model, right? So we found neutrinos have mass, okay? I said they're not left-handed, okay? So that means for every left-handed neutrino, there's a right-handed neutrino that goes with it. And for every right-handed antineutrino, there's a left-handed antineutrino that goes with it. If neutrinos are direct particles, I just added 6 states to the standard model that are gauge sterile. They don't interact with anything. They're just ghosts and don't do anything in the standard model. They're sitting there and they do nothing, right? if I believe neutrinos are Myron, I don't have to add anything. You know, my left-handed, the left-handed state that corresponds to my right-handed antineutrinos, just the neutrinos. And the right-handed state that corresponds to my left-handed neutrinos, they're just the antineutrinos. So I don't have to add anything to the standard model. So on the grounds of, you know, being parsimonious and adding the least stuff to nature to explain your results, I think neutrinos probably are Majorana particles. And I think if you polled theorists, I mean, you know, not that that is any that strong an indication, but I think if you polled theorists, you probably find 90% of them plus agree.
Thank you. Another question about the instruments. So how collimated is the neutrino beam in Japan, i.e. what's its angular spread? It must be tiny since you have to hit such a small target so far away.
Well, there's two ways to hit a small target far away. It's to have a little bitty beam and aim it really well, or it's to have a great big beam and not aim it all that well. Neutrino beam is maybe generous, all right? Because neutrinos, of course, aren't charged, so you can't make a beam out of them. So all we can do is take the pions, point them in more or less the right direction, and then when they decay, conservation of momentum means that the neutrino is more or less going in the direction that the pion was going. So we just kind of spray them out that way. The beam is, well, the fact that we aim our beam 2.5 degrees, right, off axis tells you that the beam is, is more than 2.5 degrees wide. In fact, it's by the time it gets there, it's sort of 10 kilometers wide, which is basically how we can hit the detector from so far away. I mean, it's so wide that we don't have to aim it all that accurately. Although it turns out, based on our measurements near detector, do a much better job at aiming it. A cute little trick that shows you that the Japanese think ahead. I showed you that Hyperchemiocanda is located under a different mountain than Superchemiocanda. And yet, because they're measuring the same thing, we want them to be the same angle off axis from the beam. And so the way that's accomplished is the beam is actually aimed between the two detectors. So Superchemiocanda is 2.5 degrees to the right of the beam as you look down the beam. Hyperchemiocanda is 2.5 degrees to its left. And in fact, the beam is under the ground there. It's still deep under the ground. More of the angle is down than sideways. The beam is deep under the ground there, and it comes up out of the water in the middle of the Japan Sea. And it goes through the atmosphere over the top of Korea. And that has led us to propose to put a second Hyperchemiocanda in Korea at the second oscillation maximum. So, the neutrinos are oscillating, and Hyperchemiocanda is chosen to be one wavelength of that oscillation away from J-Park. If you go 2 wavelengths of that oscillation away from J-Park, you're in Korea. So the idea is to put a second Hyperchemiocanda in Korea. And by comparing the second oscillation to the first oscillation, you can cancel out a huge number of systematic effects. It is, however, slightly expensive, so we'll see.
Okay, I know we have a lot of questions remaining in the chat at the moment, but I'd encourage most of you to go to the Slack channel. One will be created specifically for questions to Professor Wark. And I'll just read off one to finish up. Thank you everyone for coming. So the very last question is, do neutrinos interact differently with matter than antimatter? Yes.
Sadly, yes. Well, if you think about it, they would, wouldn't they? Because, at the bottom line, they're interacting with quarks. And, matter and antimatter have different quark compositions. So yes, they will interact differently. Like I said, the cross sections of a neutrino with matter and antimatter differ by between a factor of 3 and 6, depending on the energy. And so that is a big problem for us, unfortunately.
Okay, thank you so much, Professor Wark. Thank you everybody for coming. The links to recordings will be posted in the Slack channel if there were any that you didn't get the time to go to, or any that you found so interesting that you need to look at it again in order to understand the details of what was said. Again, you're welcome to join the Slack channel and ask any questions which we didn't have time for, or any that you come up with after the conference. It's been a really great opportunity to be a part of, especially since for Oxford, we haven't been able to be a part of this wonderful conference in previous years. So thank you so much for having us, Imperial and UCL. And I think Bilgisu would also like to say a few words.
Hello, everybody. Thank you all for coming. I hope you enjoyed this conference. I think we've really covered some very important cutting edge research in particle physics, and it's been an absolute pleasure to have such esteemed guests. And I hope you all enjoyed it as much as we did. And I'd encourage you to keep interacting in the Slack workspace, ask questions, talk to other attendees. And yeah, thank you everybody for coming, and see you next year.
Hi, just a few closing remarks from the UCL Physics Society. We would like to thank everyone for coming, and a special thank you to all the professors and everyone that made this possible. Special thank you to our academic officers, Lorenzo and Zara. You did an amazing job. We're so happy that this happened. Hopefully we can see everyone next year, maybe in person, if that's allowed. To finish off, we've got a talk coming up with Professor Bell Bernal on the 24th. Everyone who's a part of the UCL Physics Network is more than welcome to come. And we're going to have more events coming up in the future as well. So we hope that you can join us again. And thank you again. This was a really nice experience. Thank you, guys.